Hello, my good people. Good morning, good afternoon, good evening, depending on the time you are watching this video. Welcome again to my YouTube channel or the Big Structure Hub. This is a place where you learn, build, and innovate. Today, I want to start solving problems using moment distribution method. And I want to begin by simple frames. And the reason as to why I want to begin by simple frames is that there is one subscriber by the name Duncan Mariri. He requested me to tackle such a problem of simple frames using moment distribution method. So Duncan, wherever you are, I hope you are following this video, and let me hope this video will help you to solve your problem. So stay tuned, and for those who have not subscribed to my channel, please do so and hit that notification bell so that you may be the first person to be notified when a video is uploaded in my channel. So let's see how we can solve such a question. Solution. And before we begin solving this question, let's understand the question first. So the question reads, analyze the simple frames shown below and hence draw shear force and bending moments diagrams. So this is a simple frame. It is fixed at A, also it is fixed at C, and also at D. Again, this simple frame is loaded with 60 kilonewton at 2 meters from point A and 3 meters from point D. Again, it is loaded with a UDL of 20 kilonewton per meter. This UDL is covering 60 meters length. Again, it has 2I from A to B, and then I from B to C, and then I from B to D. So let's see how we can solve such a question. So solution. The first thing to do is to calculate fixed end moments. So fixed end moment. Fixed end moments. And how do you calculate fixed end moment? From the word fixed. So we will assume each span to be fixed. For example, span AB. So if I can draw span AB here, like that, I will assume at this point is fixed, and then at B is fixed. And then I load it, that is 60 kilonewton. This is 2 meters, 3 meters. This is point A, point B. So here we'll have moment. So fixing moment MF BA. Again here we'll have moment, fixing moment AB, like that. And I hope I gave you these formulas for fixed end moment during the introduction to moment distribution method. So if you are not familiar with these four formulas for fixed end moment, go back to my video about introduction to moment distribution method. So here we'll calculate fixing moment at AB and fixing moment at BA. So fixing moment at AB is equal to minus W, this load, times A, this distance, B squared over L squared, like that. So here, F AB MF AB is equal to minus 60 times 2 times 3 square over L. L is this distance, 2 plus 3, that is 5. 5 square. So the answer is, punch your calculator, negative 60 times 2 times 3 square divided by 5 square. So the answer is negative 43. Negative 43.2 kilonewton meter, like that. So that is fixing moment AB. Now we go to fixing moment BA. So MF BA, which is this one. So this one will be plus W A square B over L square. So this one will be W, which is 60, times A. A square is 2 square times B, which is 3 over 5 square. So this one will give you, again you punch your calculator, 28.8 kilonewton meter. So that is fixing moment BA. We proceed to span BC. So we go to BC. BC. If I can draw BC, and I show each point is fixed, like that, and then we have this. So 20 kilonewton per meter, and then the distance, we have 6 meters, like that. Then this is B, this is C. So here we'll have MF CB. Then here MF BC, like that. So we will go straight to fixing moment, which is MF BC is equal to this one. Because it is moving in anticlockwise, it will be minus WL squared over 12. So the W is a UDL, which is 20. Remember to put negative, times 6 square over 12. So the answer is negative 20 times 6 square over 12. The answer is negative 60 kilonewton meter. So we are done with fixing moment BC. We go to MF CD. So this one will be, because it is going in clockwise direction, plus WL square over 12. So is equal to plus 20 times 6 square over 12. So the answer remain 60 but positive. Positive 60 kilonewton meter. Kilonewton meter. Like that. Then you go to span DE, span DB. So DB, DB. So at DB, we'll have M, F, D, D, which is equals to 0, which is equal to M, F, B, D, because there is no any loading along this span. So there is no loading. So it means fixing moment dB is equal to 0 is equal to fixing moment BD, like that. So we have calculated our fixing moment. The next thing we'll be calculating is stiffness factors. So let's proceed to stiffness factors. And because of space, I will wrap this and also this. But these values, we'll use them later in our calculation. So we proceed to stiffness factors, which is K. So we'll have K1. So K1 is equal to KAB. KAB is this span, KAB. So as you can see, AB is a fixed beam or a span. So the formula for this, remember, is I over L. So this one is equal to I. This is I. So here we have 2I. So we'll have 2 and then L. L is this distance from here to here. So 2 plus 3, that is 5. So that is K1. K2. K2 is equal to KBC. So KBC, as you can see again, it is a fixed beam. So it means our formula remains the same, I over L, which is equal to I. I is 1. So 1 over L. Distance from here to here is 6. Like that. We proceed to K3. So K3 is KDB, which is equal to, again, this is a fixed span, so it means the formula remains the same. I over L, which is equal to uh, the I. I is 1 over L. L is this distance from here to here, 4. So this is K3. After that, we go to distribution factors. Distribution factors. Sorry, this one should be this KB B like that. And then we go to distribution factors. DF like that. So we know that distribution factor AB DF AB is equal to DF CB is equal to DF DB. DF DB is equal to 0 because these are the fixed support. So this is the fixed support or fixed end. So distribution factor AB and distribution factor CB and this distribution factor DB is equal to 0. The reason is they are fixed support or fixed end. So that is it. Then we move to distribution factor BA, DF, BA, BA. So distribution factor BA will be KBA over, so we are at BA. So we'll have KBA over KBA again plus KBC, KBC plus KBD, KBD like that. So DF DA is equal to KBA 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 is 2 over 5. So 2 over 5 over 2 over 5 plus KBC 1 over 6 plus KBD. KBD is 1 over 4 like that. And then you can punch it in your calculator and get the answer. So the answer is 24 over 49. So I will encourage you to use fraction and not decimal places because the fraction will give you accurate answer, and decimal places, if you keep on rounding and rounding your answers, it may not give you the accuracy in your answer. So use fraction and not decimal places. And if you are using such a calculator, it is easy to get your answer in fraction and not in decimal places. So we have some other calculator like the high school calculator FX82. It will give you your answer direct in decimal places. So buy such a calculator. You go to distribution factor BC, DF BC. So the FBC, BC, it will be KBC, KBC over KBC again plus BC plus K plus KAB, KAB plus KDD, KDD. So DF BC is equal to KBC is 1 over 6, is 1 over 6 over 1 over 6 plus KAB 2 over 5 plus KBD 1 over 4. So the answer is 10 over 49. 10 over 49. So that is the FBC. We proceed to DFBD. So DFBD is equal to, now you know the formula, so it's equal to KBD, which is 1 over 4, again 1 over 4, plus KAB, which is 2 over 5, plus KBC, 1 over 6. So the answer is 15 over 49. Like that. So if you want to know your answers, your distribution factor are correct, you should take this, add to this one, and add to this one. It should give you 1. But if the result is not 1, then there is a mistake somewhere. So you can take 15 over 49, 15 over 49 plus 10 over 49 plus 24 over 49. So the answer is 1. Let me show you on my calculator. So it means our distribution factor are very correct. So we proceed. After calculating our distribution factors, the next step is to draw a table, and this table, it will have joints, member, distribution factors, and fixed end moment. And then you will insert what you have calculated already in this table. So I will explain this table in detail. So under joint, you will have joint A. As you can see, we have joint A, B, C, and D. So you will have your joint here, A, B, C, and D. And then you come to members. For members, you'll have at joint A, you only have member AB. So that is AB. And joint B, we have several members. B, we have member BA, and then member BC and BD. As you can see, BA, BC, BD. And then we proceed to joint C. So this is joint C here. Joint C, we have member CB. And then we proceed to joint D. This is joint D. We have member DB, like that. And then we come to distribution factors. We have already calculated our distribution factors. They are here. So it's just to pick what corresponds to member and insert where appropriate. So for example, member AB, our distribution factor is 0. You put it 0 here. We proceed to member BA. Member BA is this one. You take what you have here and bring it here. So it is 24/49. Then you go to member BC. So this is member BC. As you can see, our distribution factor is 10/49. You pick it here and bring it here. So 10/49. And then you go to member BD. Member BD is this one. So we have 15/49. 15/49. And then member CB. CB is 0. 0 here. And then the last one, DB, 0. Put 0 there. And then we come to fixed end moment. We already calculated our fixed end moment and it is here. So pick what corresponds to member and insert in that box. For example, member AB, the fixed end moment for AB is negative 43.2. You put it there. BA, 28.8. You put it there. BC, negative 60. You put it there. You go to BD. BD is 0 because we said in our earlier calculation there is no loading along this span or this member. So there is no load acting on this member. So our fixed end moment is 0, like that. We proceed to CB. CB is this one, 60. Take it from here, bring it here, 60. And then you go to DB. Again, we said here, no loading, 0. Then from here going downward is now what is required of you to do or to start calculating by balancing, carrying over, like that. So as you can see, we have how many joints? A, B, C, and D. But on these joints, we have one joint, which is B. This B, it has several members, BA, BC, BD. It means if you can add fixed end moment of BA, BC, BC, or BA, BC, BD, it should give you 0 for this member to be in equilibrium or to be balanced. But if the total fixed end moment is not equal to 0, it means it is not in balance. So it means you should be balanced so that the final moment of these members should give you 0. So the first step to do is to balance joint B. Joint B, balance joint B. Again, some other thing to note that joint B is it has a simple support, as you can see. It's a simple support. So let's see how you can balance this joint B. So to balance joint B, we'll need to add all these fixed end moment corresponding to joint B. So you'll take 28. Let me show you. Take your calculator. We have 28 like that. Then plus minus 60 plus 0. If you press equal sign, it should give you 0 for that joint to be in balance. But if it's not equal to 0, then it means it is not in equilibrium. So like that. As you can see, our answer is not equal to 0. Our answer is negative 31.2. So negative 31.2. So we have found our answer to be negative 31.2. So what should you do to this negative 31.2 so that it gives you 0? So negative 31.2, if you take negative 31.2 plus 31.2, automatically is equal to 0. So you will take the opposite sign of negative, which is positive, and say that positive 31.2 should be distributed equally to each member of joint B. So we are going to distribute positive 31.2 to each of these members, member BA, BC, BD, to make this joint B be in balance. So how are we going to do it? You'll take positive 31.2 times the distribution factors of these members, of each of these members. For example, we begin by member BA. So you take 24 over 49 times 31.2, 24 over 49, like that. So let me show you. And then equal sign. So the answer is 3744. 3744 over 245. We proceed to joint member BC. You take 31.2 times 10 over 49, like that. I will show you on my calculator. So the answer is 312.49. 312.49. You proceed to member BD. You take that 1.2 times the distribution factor, which is 15 over 49. So the answer is 468. 468 over 49. You write it here. After every balancing, you will be carrying over whatever you have balanced. So you carry over by taking a half of this to the opposite member. For example, member BA. The opposite of BA, member BA, is AB. So you take this value, you divide by 2, or you multiply by a half, and carry it over to the opposite member, which is AB. So as you can see, we have that 7. Let's do it practically. That 7, 44, divide by 245 times 0.5. You can either divide this value by 2 or multiply this value by a half, or multiply by 0.5. It is the same thing. So it gives you 1872,245, and you write your value here. You come to BC. So the opposite member of BC is CD, this one. So you'll take a half of this to the opposite member, which is BC. So 312 divide 49, multiply by 0.5. You will get 156 over 49. Check it on my calculator. 156 over 49. So you will come and write it here. And then the opposite member of BD is DB, this one. So you will take a half of this and carry it over to the opposite member, which is DB. So 468 over 49 times 0.5. So that is 234 over 49. 234 over 49. So this is the value, you write it there. And then, as you can see, there is no any further progression from here because there is no any other joint you can balance. So the next thing is to find the final moment. So the final moment, you will add from here, from fixed end moment, you take this, add this, get this, the final answer. So negative 43.2 plus 1872 over 245. So the answer is this one. And then from there, you can write your answer in decimal places. So that 5.56, negative that 5.56. Here it is. Again, you come to this one. You take 28.8 plus that 7.44 over 2.45. So the answer is this one. Because we want our answer in decimal places, that is 44.08. 44.08. Again, you take this one. Negative 60 plus 312 over 49. So the answer is 53.63. Here it is. Again, 0 plus 468 over 49. 0 plus 468 over 49. Again, our answer is this one. Because we want our answer in decimal places. 9.55. Here it is. Again, you come to this one. 60 plus this, you will get this one. 0 plus this, you will get this one. So we can now check if our number is balanced or not. And how are you going to check? You will take this one plus this plus this. All members of joint B, the sum of fixed end moments should give you 0. So 44.08 plus negative 53.63 plus 9.55. So the answer is 0. So it means our final moment is correct. We proceed. Allow me again to wrap this to create a space for more calculation. So let me wrap this. Let's now indicate our moment, our final moment we have calculated on our simple frame. So we had that 5.56, that was moment AB. So this is A, this is joint A, B, C, D. So our AB was negative 35.56. And we said in our sign convention, anti-clockwise moment is treated as negative. So as you can see, this moment is moving in anti-clockwise direction. And then we had BA, BA as positive 4.08. So this one is moving in clockwise direction. And then we had negative 53.63 in anti-clockwise direction, as you can see. And then we had 9.55, that is BD, 9.55, positive again in clockwise direction, as you can see, 9.55. And then we had 63.19, it was positive in clockwise direction, as you can see, 63.19. And then we had 4.78, it was positive in clockwise direction. So this is how we indicate our final moment on our simple frame. Now we proceed to reaction. We will calculate the reaction. And how are we going to calculate the reaction? So this is how we're gonna calculate the reaction. So you will take this joint, split here like that, again split like that. This is A, so this is RA, this is RB1, RB2. Come here, that is C, that is RC. So we have loading here, which is 60 kilonewton. So this is 2 meters, and this is 3 meters, and this is 6 meters. Again, we have 20 kilonewton per meter as a UDL. Again here, we have moment 63.19. We have moment again 53.63. We have moment 44.08. We have moment 35.56. Like that. We are not interested in this portion because there is no any loading along this span. So we begin by calculating our reaction by saying that summation of moment at A is equal to 0. So 2 plus 5, 2 plus 3, that is 5. RB is moving in each direction. And so negative 5, RB1, we come to this moment, it is in anti-clockwise direction, minus 35.56. This loading 60 in clockwise direction plus 60 times 2. This one moving in clockwise direction plus 44.08 is equal to 0, which imply RB1 is equal to, you can carry out the operation by yourself and find RB1. So RB1 is equal to RB1 is 25.70. 25.70 kilonewton. Then Ra is equal to 60 minus 25.70. Summation of upward forces is equal to summation of downward forces. That is the reason. So Ra is equal to 34.30 kilonewton, like that. 34.30 kilonewton. So we proceed to this portion. So under this portion, we'll sum again moment at RB2. So summation of moment at RB2 equals to 0. So RC is moving in anti-clockwise direction. So minus 6 RC. We come to this moment, which is 53. It is moving in anti-clockwise, minus 53.63. We come to a UDL, which is 20 kilonewton per meter. In which direction? Clockwise, plus 20 times 6 over 3 over 2. So we are multiplying by 6 to change it to a point load, and then the moment act at the center, like that. Then you come to this one. In which direction? Clockwise, plus 63.19 is equal to 0. So if you can carry out the operation correctly, you will find that, which imply RC is equal to, let me punch my calculator. So the answer is 61.59 kilonewton. So that is RC. So RB2 is equal to 20 times 6 minus 61.59. So summation of upward forces is equal to summation of downward forces. That is the reason for that. So this one will be 120. So 58.41 kilonewton. So this is our RB2. So it means RA is equal to 34.30 kilonewton. RB equals to RB1 plus RB2. RB1 is 25.70 plus RB2. RB2 is 58.41. So this one will be 25.7 plus 58.41. 84.11 kilonewton. Then RC is equal to RC 61.59 kilonewton. We can proceed and draw the shear force diagram. So let me create space here for shear force diagram. Let me create space here. So shear force diagram. So this is our beam for shear force diagram. So we have at A, this is A, this is B, and this is C. So at A, we have reaction at A, we have 34.30. So we'll approximate along this line. So that is 34.3. At 4.3. So you'll take your calculator, take that 4.3, come to this loading, which is 60. It is acting on a beam which is downward, so minus 60. So it gives you 25, negative 25.7. Approximate below the baseline. So let's say like there, and then there. So 25.7. And then it will be constant up to the next force, which is reaction at B. So take negative 25.7 plus a reaction at B is 84.11. So it's give you 58.41. Approximate again along this line. So that is 58.41. And because this is a UDL, it will be a diagonal line. So 58.41 minus 20 times 6. That is 61.59. So 61 around there, 61.59. So it will be a diagonal like that. And then negative 61.59 plus RC, it brings you back to 0. This is 0. So this is positive, negative, positive, negative. So that is our shear force diagram. So the next thing to do is to calculate moments. So before you start calculating moments, let's determine these points. That point. So this is point Y, and this point is very important because it gives us the maximum shear force. No, the maximum bending moment at this point. So we have to determine this distance. So this is X, and this one will be 6 minus X. So for you to determine the value of X here, you can either use similar triangle rule by taking this value of X, you divide by 61.59, and then you equate to 6 minus X over 58.41, and then you form an equation and find the value of X. Another way of finding the value of X is that we know that at this point, the shear force changes from positive to negative. And at this point, the shear force is 0. So you will form an equation either from coming from this side or from this side to where our shear force is 0. So let's start from this side. So to form an equation, you will take the upward forces to be positive and the downward forces to be negative, and sum them and equate them to 0. So Our upward forces here is reaction at C, which is 61.59. 61.59. So from here to here, we have a UDL of 20 kilonewton per meter, but we don't know the distance. The distance is x, and for you to uh, get a point load from a UDL, you multiply by distance x. So minus 20 times x, what the distance is x, is equal to 0. So 61.59 minus 20x is equal to 0, which imply x is equal to 3.08 meters. So this distance is 3.08 meters. And the remaining distance, you get the difference between 6 and 3.08, which is 2.92. So this distance is 2.92 meters, like that. So now we can calculate our bending moment at various points. So bending moment at A. So bending moment at A, we had already calculated, or we already have bending moment at A as 35, negative 35.56 kilonewton meter. Bending moment at this point, let's say E. Bending moment at E is equal to bending moment at A, which is negative 35.56, plus the area of this one. So this one will be 34.3 times 2 is equal to, punch your calculator, 33.04. Bending moment at B, we already know bending moment at B. No, we don't know the bending moment at B. So the bending moment at B will be bending moment at E, which is 33.04 minus the area of this. So minus 25.7 times 3. So this one is equal to negative 44.06. Negative 44.06 kilonewton meter. Like that. Then you go to bending moment at Y. Bending moment at Y. Let me wrap this to create a space. So bending moment at Y, bending moment at Y, it will be bending moment at B, which is negative 44.06 plus this area, so plus a half times 58.41 times 2.92. So the answer will be 58.41 41.22 kilonewton meter. Then bending moment at C will be bending moment at Y, which is 41.22 minus the area of this, which is a half, times 61.59 times 3.08. So minus 0.5 times 61.59 times 3.08. So 53 negative 53.63 kilonewton meter. Now we have our bending moments at various points. We can now draw our bending moment diagram. And this is how we draw our bending moment diagram. So to draw bending moment diagram, you will draw first the original frame. As you can see here, this is the original frame. So we have 60 kilonewton. This was point A. Maybe I can do this. This was A. This was B. Now this was C. This is B. And this is D. So this is the original frame. And then just extend the line like that to allow you draw a shear force, no, a bending moment diagram. Then you will start drawing. At point A, you have negative 35.5. After extending this line from the original photo, no, from the original simple frame, you can locate bending moment values at their respective points. So if you can check our table, and also you can use this calculation here. If we begin by point A, our point A, we had negative 35.56. So you locate above the baseline, 35.56, and you mark that point. You proceed to, at point E, at this point, locate where, or approximate where you think that 3.04 is. So there, and write it at 3.04. You proceed to point B. At point B, we had three moments. If you can check on our table, we had 44.08, which was positive. 44.08 or 06 is this one. Again, we had negative 53.63. It is along this line. And then we had 9.55. So 9.55 is along this line because it is BD. So BD, you approximate 9.55. And then we proceeded to point C. At point C, we had 63.19. Your approximate is here, 63.19. And then the last point is point D, member DB, we had 4.8 approximate. And then you just join these points. So from here is an inclined line, from here to here, an inclined line, and then you proceed to this. And then because this one is a IODL, it will be a smooth curve like that to this point. And then you come to this, join from here to here. And we are done with our question. And our question ends there. So let's meet in my next session. And don't forget to subscribe, like, share, and comment. Thank you for your time.